Hello everyone, welcome to Engineered Learnings. Engineered Learnings has been created as an effort to help and reach out to all the engineering students, aspirants and professionals out there with the basic understanding and the crux of the topics important for placements, Vivas, semesters, competitive examinations and all types of interviews. So let's go to today's topic. Specifically, countercurrent absorption, a very important topic for GATE, for semester examinations. Frequent questions have come from the graphical approach of countercurrent absorption or co-current absorption in GATE. So we received a mail a few days back from one of our subscribers to describe the process of absorption. So we have decided to make 4 different videos on co-current absorption, countercurrent absorption, co-current stripping and countercurrent stripping. We're going to come with all of those videos in subsequent weeks. First, today we are going to talk about countercurrent absorption. We need to understand the process. That's why we need to specifically focus on each of the processes. So first, talking about a countercurrent flow. Coming to the topic straight away. What is a countercurrent flow? We need to understand co-current is something that the 2 streams are flowing parallel to each other and entering simultaneously and exiting simultaneously. Countercurrent flow is a type of flow wherein one stream is going in this direction and the other stream is going in anti-parallel direction, not in a parallel direction but an anti-parallel direction to the other stream. Now in this case we are seeing a condition where air plus ammonia gas stream is flowing from bottoms to the tops of the absorption tower. This is the absorption tower. And a pure water stream is flowing from the tops to the bottoms of the absorption tower. Now what is happening is, in the process, some amount of ammonia is getting absorbed from air to water, and we are considering the assumption that no water is getting transferred to air or no air is getting transferred to water. Only pure ammonia is getting transferred from the air stream to the water stream. So in the process what is happening is, air with a high amount of ammonia is going from bottoms to tops, that is entering the first plate, so it is Y1 and G1, total gaseous flow rate of entering the first tray is G1, and the mole fraction of the NH3 in that gaseous stream is small y1. So it is exiting at from the nth tray going to the n+1th tray hypothetically, which is not there. So it is Gn+1 to Yn+1. Mole fraction of NH3 in the coming from the nth tray is Yn+1 and the total flow rate, gaseous flow rate, is Gn+1. Now this NH3 is much low because comparatively to this, because some amount of NH3 has transferred from gaseous stream to liquid stream. So this is the thing that is happening. So we are getting a clear view of the process. Air and NH3 entering from bottoms, going to the tops. The NH3 exit concentration or mole fraction is much lower than the inlet concentration or mole fraction of NH3. And for water, pure water is entering. So Xn is equals to 0. In this process, we are considering that Xn is equals to 0. So it is pure. That's why no mole fraction or no traces of NH3 is present in the incoming water, whereas there is a sufficient quantity of NH3 when it is exiting. So it is exiting as water plus NH3. It is coming as pure water, exiting as water plus NH3, water plus ammonia. So if we strike the mass balance of this entire column, let us strike the mass balance, we get that Gn+1, that is first the exiting streams, this is the outlet stream, and this is the inlet. So inlet NH3 is equals to outlet NH3. We are striking the NH3 balance. This is the NH3 balance. NH3 balance. So inlet stream, how much NH3 is coming with the inlet stream? It is G1Y1 plus NNXN. Xn is 0 in this case because no NH3 is present in the pure water. So mole fraction of NH3 in pure water is 0. So this will correspond to 0. So G1Y1 plus NNXN is the incoming NH3. Its amount of Xn, its amount of NH3 is present, that is not pure water. So some small stresses of ammonia is present in that water. This Xn will have some value other than 0, some positive value. So it will add up to the incoming NH3 in the absorption tower. Now outgoing NH3 from the absorption tower is nothing but from the nth tray what amount of ammonia is going out? That is the total flow rate into the mole fraction of the ammonia coming from the nth tray, and from the first tray the ammonia that is exiting from water, so L0 X0. So total liquid flow rate into the mole fraction of the ammonia in the liquid flow rate. So this is the total outlet is equals to total inlet. Now we are seeing that in this process we cannot draw a proper slope in between the exit and the inlet concentrations, because the total gaseous flow rate or the total liquid flow rate is also varying. Like it is L0 here and Ln here, because the total flow rate from Ln has increased to L0 because some amount of NH3 has been absorbed and it has affected the total flow rate. So if we go and work with the total flow rate and the mole fraction, we are never going to strike a steady balance, or we will strike a balance, but we are not going to get a simplified form of the equation, because this gaseous flow, total gaseous flow rate and the total liquid flow rate is keeping on changing throughout the process. So we have to work with parameters rather constant. That is, the gaseous flow rate should be such that it should remain constant. So to strike a simplified form, what we have done is we have considered G dash and L dash. What we have given the definition of G dash and L dash as it is written here. G dash is the moles of air flowing and L dash is the moles of water flowing. Now, as we have already mentioned previously that there is no transfer of air from air to water and no transfer from pure water into air. Only NH3 is getting transferred. So G dash and L dash remains constant. And what we have defined as capital Y rather than small y is the mole ratio and not the mole fraction. But what is the mole ratio? Mole ratio is nothing but moles of NH3 by moles of air and moles of NH3 by moles of water. So capital Y is nothing but moles of NH3 by moles of air, and small y is moles of NH3 by total moles. So what we have done is we have simplified the form, we have given moles of air. So this is constant. So when we multiply this with this, that is G dash with yn plus 1, what happens is moles of air cancels out, and we get the moles of NH3 present in the gaseous stream. So we can see that outlet stream has G dash yn plus 1 NH3, agreed, and outlet stream from here will have L dash into X0, because X0 is having NH3 by water in the outlet stream and L dash is having moles of water in the outlet stream. So again cancels out and gives moles of NH3 going out with water. And inlet stream J dash Y1 plus L dash Xn, as we can clearly see. Now when we solve this equation, we get an operating line equation of Yn plus 1 minus Y1 by Xn minus X0 is equals to L dash by G dash. Now what is Xn minus X0? That is mole ratio difference from the inlet to the outlet stream. And similarly, mole ratio difference from the inlet to the outlet stream, the gas is present here. And this is an absorption process. Now what is happening is, if we draw it graphically, if we draw the operating line graphically, this is the slope of the operating line. This is the slope of the operating line. So if we draw it like corresponding, X0 and Y1 are the corresponding points, Y1 and X0. So we get something like that. This is X0 and Y1, this point supposedly. Because X0 has sufficient amount of NH3, Y1 also has sufficient amount of NH3. So it will be somewhere here, X0, Y1, going to the first string or coming from the first string. And then the concentration varies and exits at Yn plus 1 Xn. Now, at this point of time, the Xn I have considered it to be 0. If it is not 0, it will end up somewhere here. So it will have an Xn value and it will have a Yn plus 1 value. If it is not 0. If it is 0, it ends here only. Xn is equal to 0 and Yn plus 1 is having some value here. So some amount of NH3 is still remaining there. Now what happens is, for a defined system, now if we see what is happening is, Yn plus 1 minus Y1 by Xn minus X0 is L dash by G dash. So this is defining the operating line, and the slope of the operating line is L dash by G dash. Now there is an equilibrium line. What is the equilibrium? Let us understand the concept of equilibrium. Before going to the equilibrium, let us understand the saturation concept. So what is saturation? Saturation is a state beyond which the liquid cannot further absorb NH3 from the solution. So if I know, supposedly, if I know that my Y1, that is the entering stream, has this much ammonia within itself, that is this much mole ratio of ammonia within itself, I can actually predict the outlet, the maximum outlet concentration or the mole ratio possible in the water that is exiting from the equilibrium equation. Supposedly this is my equilibrium line. When it reaches equilibrium, no further mass transfer will occur from the gaseous state to the liquid state. So at this particular y1, if I drag this point and touch the equilibrium line, so whenever it touches the equilibrium line, the corresponding x value will be x saturation. That is, see, this x0 is lesser than x saturation presently. So maximum what can happen if we keep on increasing, if we touch this equilibrium line, beyond this equilibrium line, further mass transfer cannot occur. So till this equilibrium line, that is till x sat, if we maintain proper conditions, if we increase the height of the tower, if we maintain proper conditions, x saturation, x sat is the maximum value that this water can have, the amount of NH3 that it can have. So x sat. So if we know the y1, if we know the equilibrium data, we can calculate the maximum saturation mole ratio that can be present in the liquid stream. And many questions are popped out in GATE from this, that calculate the saturation mole ratio, saturation mole fraction of ammonia in the liquid stream. So you see this. Now what is the significance of this equilibrium line? Let us understand this. Let us understand what is the significance of the equilibrium line. So we see that what is happening is, this is the transfer that is happening. So this mole fraction, the mole fraction or the molar ratio in the gaseous stream will be high enough. It will decrease to the interface wherein the mass transfer is occurring from the gaseous to the liquid phase. That is, if we take a droplet, supposedly this is my air plus NH3 and this is my water plus traces of NH3. So air has a high amount of mole ratio of NH3 high, which further decreases to equilibrium. As we shift towards the liquid phase from the gaseous state, the NH3 concentration is decreasing. That's why the mass transfer is occurring. NH3 is lesser in the liquid state than in the gaseous state. So it will touch an equilibrium or interfacial concentration. This is the interfacial, that is phase between the gaseous and the liquid state, interfacial concentration or interfacial mole fraction or interfacial mole ratio. After that, what will happen? It will go to x, that is, further it will decrease in the liquid state. So as we go from the vapor or gaseous phase to the liquid phase, the molar ratio keeps on decreasing and decreasing and decreasing. So this is what it states. Now, how will you understand it is an absorption process or a stripping process? If the operating line is above the equilibrium line, so if we draw a slope of minus kg by kl, drop a slope of minus kg by kl to the equilibrium line, we get the interfacial concentration. So what is happening is, interfacial concentration, if you see, yi is always lesser than y if my operating line is above the equilibrium line. The yi, the interfacial concentration, will be always less than y. In that case, it is pretty clear that mass transfer is occurring like this from the gaseous state to the liquid state. So it is not a stripping operation, it is an absorption operation. Absorption is clearly signified by y greater than yi and xi greater than x. This is absorption. And for stripping, just the opposite. That is, liquid will have a higher x. It will decrease to xi and further it will decrease in the gaseous state. So it will have higher ammonia in the liquid state. So for absorption, always remember this. This is how you determine. So if the operating line is above the equilibrium line, this is how you determine that it is an absorption equation. It is the absorption process that is taking place. So we have understood the concept. We have understood the concept of equilibrium or the interfacial concentration, how it is occurring. And we have also understood that what is the maximum amount of mole ratio of, that the maximum amount of NH3 it can take. That is, for a given Y1, that is a given moles of NH3, the maximum moles of NH3 that may be present in the liquid solution is exact saturation when it touches equilibrium. Now to achieve that, what we need to do? What are the conditions we need to maintain? We just need to decrease the slope to here. So we get the new slope as L dash by G dash, where L dash new is always less than L dash old. Now this L dash, for this L dash, the old slope was always higher than the new slope. So L dash new, the slope will be always less than the slope new will always be less than the slope old. As is clear. That is lower liquid flow rate, or rather a higher gaseous flow rate. Also, it may happen if the L dash is constant. So G dash new is going to be higher than G dash old. So higher gaseous flow rate and lower liquid flow rate ensures that the curve is tipping and touching the equilibrium line. So to maintain good conditions for absorption, we need to maintain a lower liquid flow rate and a higher gaseous flow rate. So the lower liquid flow rate and higher gaseous flow rate has to be maintained. And we have already understood the concept of equilibrium concentration. So this is how exactly stripping is operating. Now, you may question that the equilibrium line, where do we get the equation from? The interfacial concentration. Equilibrium line equation is yi is equals to kxi. K is a constant slope. So you may question that equilibrium, why have you drawn a curve? It should be a straight line. This is small y. Remember, this always also pops up as a question. Always convert the mole fractions into mole ratios whenever you are working with absorption equations. So we see y is equals to moles of NH3 by moles of NH3 plus air. Okay, total moles. Capital Y, as we have described, is moles of NH3 by moles of air only. So if we strike a balance, it is nothing but capital Y is equals to small y by small y minus 1. Or rather, small y 1 minus small y. That is, if we do moles of NH3 by moles of NH3 plus air, 1 minus moles of NH3 by moles of air, so it's going to strike a balance. So moles NH3 by moles air by moles of air plus NH3, and this will ultimately cancel up. It's getting a little fuzzy, so let us do it like moles of NH3 by moles, total moles, let's say total moles by moles of air, that is 1 minus y. 1 minus y is total moles minus moles of NH3 by total moles. This is 1 minus y. So total moles cancel. Total mole minus moles of NH3 is moles of air. So capital Y is moles of NH3 by moles of air. So you remember, always remember this formula when you are going for a gate or semester examinations. That is, capital Y is equals to small y by 1 minus small y. And small y is equals to capital Y by 1 plus capital Y. So if we consider this equilibrium equation for capital Y, it is going to be yi by capital Yi plus 1 is equals to xi by capital Xi plus 1 into k, if I consider this. So this is what the equation is like, and that is why it is not a linear equation, it's a non-linear equation. So that's it, countercurrent absorption, that is it all about. To sum up, we know that air and NH3 is flowing into the system from the bottoms, water is coming from the top. The NH3 concentration in the water is 0, that is the mole ratio and the mole fraction both are 0 at this point of time. When it crosses each other, transfer is taking place. NH3 is going from air to water, no water is flowing to air, no air is flowing to water. So air exits with a lower mole ratio of NH3 from here, and water exits with a higher mole ratio of NH3 here than compared to here. Since it had no NH3, so NH3 has got transferred from air to water, and in the process we are seeing that what is happening is, at this point of time, the water is having a high NH3, the air is having a high NH3. So it is x0 and y1 at this point of time. Water is having no NH3, so xn is equals to 0 for pure water, and air having some amount of NH3 that is remaining, that is not transferred. So it is yn plus 1. And if we strike a balance, we get a slope of L dash by G dash. If we draw minus Kg by Kl, we get the interfacial concentration, by which we determine that it is an absorption equation by that thing we have already shown, that how the interfacial will vary. How we can decrease the slope, how we can vary the L dash or the G dash, that is the liquid fluid and the gaseous fluid, to touch the equilibrium line such that maximum mass transfer occurs, such that this exits at exact, that is the maximum mole ratio of NH3 present in the water that is possible given a particular Y1, particular inlet mole ratio. So it touches, and exact is the mole ratio, that is the maximum possible mole ratio. So this is the countercurrent absorption all about. This is how you graphically approach it. It is always, the equilibrium line is always below the operating line. The operating line can have a minimum slope of the slope such that it touches the equilibrium line. Very important, the question has repeatedly come from this section, that what is the minimum liquid flow rate. So if we decrease the liquid flow rate, it will touch the equilibrium line. So if we know all the equations, like if we know, supposedly you are given a question like this, so you straight away, you know y1, you know xn is equals to 0, you know yn plus 1, that is exit. What you don't know is what will be my value for minimum, supposedly minimum L dash by G dash we know. So when we go for the minimum L dash by G dash, supposedly we do not know. We know the equilibrium constant, so we know that y1 is equals to y1 by y1 plus 1 is equals to k into x sat by x sat plus 1, as we have already shown for the equilibrium line. So from here we find out the maximum x sat, that is the maximum x value x sat that is possible, because we know y1, we find out x sat, we know yn, we know yn plus 1, we know xn. From here what we do is we find out the slope, that is L dash minimum by G dash is equals to slope, which is equals to again yn plus 1 minus y1 by x sat in this case, or rather xn minus x sat. So we know x sat, we know xn 0, we know yn plus 1, we know y1. We are going to find out L min by G dash. Now you will be given a G dash value. You need to just find L dash min. So that is the minimum liquid flow rate that is possible in the absorption tower. This is how you solve these problems. These are very common problems. So that's it for today. Next week we will come up with co-current absorption or countercurrent stripping as it favors. So we'll have 4 videos regarding absorption and stripping. If you liked our video, share it to your friends. Thank you very much.